So now here goes. So here are some practice examples, right? And for the most part, I may put in some different complexity classes for here, this part right here. But overall, you should be able to figure them out. So, the smallest time complexity that you would put here would be the one that has the least number of steps, right? That's a hint. But you should also have an example of what that thing is. Now, coming down here, one second. Okay, coming down here. So here we have the function x cubed, where x is a total, or I'm sorry, is a whole number, right? Would f, our set of y values, be partially ordered? And is it a total linear ordering? Explain, right? This is stuff you need to know when it comes to, being able to, I guess, feel your way around the subject of analysis of algorithms, because we're always dealing with sets and orderings and things of that nature. You've seen it already, right? Now, here's an interesting one here for number three. I'll give you a hint. The two of them are not necessarily the same. Let g of x equal 1 over x cubed, where x is a whole number. Would g, our set of y values, be a partially ordered set? Is it a total linear ordering? Explain. So you need to know the difference between partial orderings and total linear orderings. How many people remember the answer to that? Can somebody remind us what a partial ordering is? Okay, I'll give you an example. Wait, Jahid, were you about to answer, or are you just unmuted because of your last question? Mr. Allah? Allah? Okay, remuted. That answers the question. All right, so I'll give you a hint, right? If I were talking about something like, say, n, the set of all natural numbers, or z, the set of all integers, those would be a total linear ordering. If I talked about something like q, um, or let's see, I guess to some degree r, right? So if I was to tell you about r or q, you know, in those cases, I would say that they're partially ordered, but they're not total linear orderings, right? Anybody have a guess as to why? Okay, Evan.
Because with something like Q, which or anything other than like a natural set, like I think the difference between a partially ordered set and a total ordered set is that a partial ordered set is um the elements inside of that set are ordered, but there's possible other, values that could be in that set that are not actually a part of it. And that's why it's partially ordered and not totally ordered.
Okay, that's interesting. That's a good one. All right. Other people. By the way, he's not quite wrong. He's very, very close. It's just he's short of one thing. But that's like a 99% answer. Evan, you want to correct
Oh,
yourself?
thank you. Actually, that's great. But just so I can have down the correct answer, could you let
Huh?
me know at the end of this, like what the correct perfect definition is? Because I think it'd be great to know.
Okay, so here we go. So the first one, actually, you know what? Look at these closely, and you'll notice just one thing that's different. So this was x cubed, and this was 1 over x cubed, right? Something like that. Do you see anything there? Like we could, when it comes to fractions, can we put them in order? Let's
Oh,
break it.
well, I mean, the difference between f of x and g of x, right, is that you're never going to have all of the fractions inside of a list because there's an infinite number of possible things in between, um, you know, in between two natural numbers, there's an infinite number of fractions.
That's a really good one. Did you take theoretical computer science?
No, I took I took like 10th grade like algebra 2, I think.
Okay, so here's the thing. When we're talking about infinity, believe it or not, integers and fractions are the same size.
Oh, okay. That's
Yes,
interesting. This is from
it's a
many years
subject.
ago at this point, but it's just like I remember about different types of infinities.
Yeah, there are different types of infinities. And yes, Kevin, the midterm is on Monday, but we're going over the material, so not to worry. So there are different types of infinities, right? And you're aware of that. So let's suppose that we talked about, I'll just show you reducibility among a number system. There we go. That way we could kind of like redirect what that answer of yours was. Um, Yikes, but do they have the answers here? All right, here, let me help you out. Reducibility, and then I'll say integers and rationals. And let's see if they have like a real good breakdown.
I'm a little confused.
Yeah.
Question the question was asking about like the partial ordering and how
hmm
exactly what makes it partially ordered.
hmm Yeah. Yeah.
I I don't think does the amount of elements matter? I because from my understanding, he's talking about partial ordering like the what makes partial ordering partial ordered is that it doesn't have all the elements or that there could be other elements in between.
Mm,
But I
it's not the matter. Okay, so here I'll put out another hint. It's not about the elements in the set so much as it is about the property of ordering. All right. And we got people talking in the chat, like, Um, no, I didn't post it up yet. I'm still going to add in a few more questions while we discuss this. So you're seeing it right now, and you'll see it like, after the class ends. But here goes. So, um, all right. So here's how we do this. Is Z at any point ever undefined? The integers.
the integers are not undefined ever.
Okay. Ever. Right. So no matter what elements we pick out of Z, we could always order, like order them. Right? So there's no place where the idea of ordering breaks down or could break down. Now, when it comes to fractions, yes, we could order them. But now here's the question. Are fractions ever undefined?
Yeah, when would equal to be zero. I see. It's saying x being any whole number, and if g of x, the function has any asymptotal or I think antisymmetric, it's called,
Hmm,
right?
interesting. Interesting. Okay, so here's the thing. With the exception of where uh, G is undefined, you can still order any pair of numbers. But the thing is that, you know, there are undefined components in G by virtue of the fact that, we chose that particular number system. And since fractions are, a subset of the real numbers, we have decimals and whatnot, even R, the set of all real numbers would be a partial ordering, but not a total linear ordering, right? So that's what that's the outcome of that. All right. That's how that there works. So I'm asking you about partial orderings and total linear orderings, how to know what's what, and can you explain when to expect the total linear ordering and when not to? So now, Evan, do you have a question that your
Yeah,
hand was
it's just
still?
clarification. So just to make sure, f of x is a total linear ordering, while g of x is a partially ordered set.
Right. So both of them can be. Let's suppose that I just said, "Hey, do they have ordering properties, or are they both partially ordered?" The answer would be yes to both of them being partially ordered, right? But
Well,
F is
yes,
a
I see what you
total.
mean, but only
Mhm.
the f of x is also, in addition to being partially ordered, is it total ordered.
Exactly. Right. It's the
Okay,
out of the two, it's the only one that can be considered a chain or a total linear ordering. Yeah. Uh-huh.
this is maybe like a theoretical computer science question, but would you say that if a function is totally linear ordered, it is also partially ordered?
Yeah, that's true. But the
Okay,
thing is
thank
that,
you.
right, the reverse is not true though. So
Yes,
that's
I see, I
right.
see, I see. Because I guess you can think of it kind of like squares and rectangles, right? Like all squares are a type of rectangle, but not all rectangles are squares.
Roughly speaking, right. But in this case, so let's, if you wanted to break it down that way, then it would be the reason why, right? It's not just the first principle, but it would be the reason why. So a square is a special case of a rectangle where all of the dimensions are equal, right? Whereas with a rectangle, it's just a quadrilateral where, you know, there are perpendicular angles for each corner, right? So um, you wouldn't say that the dimensions are equal, right? So that part would break down. It can't fit the definition of a square. So that the same thing here. G of x, it breaks down because there are points where it's undefined. So if I pick like 1/0 and I want to compare it to something else, that's not going to work, right? If it were, however, f, and I'm just comparing 0 to something else, that does work. So that's why, one is partial only, but the other one is total. So there's no undefined, there's no gaps in it. You might say the definition does not have any gaps or exceptions. Okay, so I guess we did the whole thing with that and explaining. You can expect to see more like that. But now here's another one, all right? Because not everything is numbers. And I said here, let S be equal to the set containing B, C, and D. What would its power set P of S look like? Is there a partial ordering property on S given its subsets explained? So now what?
I'm I'm a little confused. Did we
Hmm?
talk about power set ever? I don't remember hearing about it in this class.
Okay, so let me help you with
Yeah, I
that.
don't remember either.
It's a good thing you're saying this. So remember that when I talked about no, that's something else. So on the first day, or on one of the first days, let me just make sure that I open up everything. Refresher. Remember when we talked about the Cartesian products and there was that part where I talked about subsets?
Was this on the first day of class?
It was like day 1 or 2. Do you remember when we talked about binary relations? I said reflexive. We know that there's a binary relation if something is reflexive, antisymmetric, intransitive.
I only remember that in relation to talking about the partial ordering properties.
Right,
Not
because we were right. Examples include less than or equal to.
not specifically like binary relations. I think I just
Right,
that
right,
was there.
and that's how partial orderings are established. right? So here you have a binary relation, and we know that this binary relation functions that way. So now, if we have this binary relation and we apply it to a set and it works out that way, then we can actually start to order things. Now, the same thing with subsets, right? Also, reducibility, reachability in graphs. So those were some examples, okay? Um, but I tell you what, if you want to look along right here, right now, let me open up the chat and help yourself to the refresher. Everybody got that? You should see it in the chat box. The file should be in there.
I don't see anything in the chat or Dropbox.
Okay, well then I'll do it again. Let me just see. So here you have, okay, let me just, all right, now tell me.
Yes, I see it now.
Okay, so looking along, remember that when we compare things together, so this goes back to what we were just talking about. All right, just gonna go back to like the sample questions. Sample questions. So this part here, you intuitively found the answer for partial ordering because um, it's not very hard to see how the numbers are related. But now that numbers aren't always a part of what we have in computer science. Because computer science derives so heavily from math, logical relationships also carry over. So when we have sets, now the question is, well, what if one element is a subset of another? Remember that? I asked about reflexivity, transitivity, symmetry. If A is a subset of B and B is a subset of C, is A a subset of C? Yeah, no. Hmm. A is a subset of B. B is a subset of C. Is A a subset of C as well?
I'm I'm a little confused.
Hmm. Why is that?
You're talking about E and C. Are these like sets on screen that we can't see, or just saying?
I'm just saying in general, if A were a subset of B, regardless of their sizes or their exact membership, let's just suppose that, we could take it on as a given that A is a subset of B and B is a subset of C. Would A then be a subset of C?
A is a subset of B, and C is a subset of B.
Okay, let me just go back to
Yeah, if you could type it out exactly, that would be appreciated.
okay. So here we go. Let's suppose that B star and B cross are subsets of B1. Now remember we had this whole thing talking about Cartesian products or whatever. So now we're talking about subsets. If B star is a subset of B cross and B cross is a subset of B star, that would imply that B star and B cross are one and the same. So they're subsets of one another. They're not necessarily proper subsets of one another because the nature of their subset relationship, well, neither one is a proper subset of the other because the nature of their subset relationship is based on equality. So, we wouldn't count it as a proper subset if it was either an empty set or the same exact set itself. right? So in this particular case, you know that they're equal. But now, what if B was a subset of, I mean, B star was a subset of B cross, and then B cross was a subset of B, the larger one? Now, is B star a subset of B? Okay.
I'm sorry, repeat the question again.
So let's suppose that, okay, well, let's see. Transitivity. Here you go. Take a look at this. If A is related to B and B is related to C, then A is related to C. Let's suppose that the relation was the subset relation. So if A is a subset of B and B is a subset of C, then is A subset of C?
Yes.
There you go. Right. Because one is part of a larger whole, which is part of an even larger whole. So that smallest item is also a subset of the largest collection. Make sense? Evan, question.
Yeah, I think a good example to show this is you could say that C is the set one, two, so you could say A is the set one, B is the set one, two, C is the set one, two, three.
Okay. Yeah, so A would be a subset of B and B was a subset of C, and then A is also a subset of C. That works.
Exactly.
Right. Everybody still with us?
Yeah, it would just be helpful if you could type out because I'm just having trouble following along with exactly like the what you're saying.
Examples include, so take a look at all of this, right? Examples include less than or equal to, subsets, reducibility, reachability, and graphs. So now let's take a look at what that would mean, right? If we say that those examples include just that. Well, what that tells us is that just as you were comfortable with the less than equal to on integers, you can be equally comfortable about the subset one on sets, right? Kind of like when Evan gave us his example, he didn't like stutter all through it and then flinch at the end, because once you start to see the relationships, you know that once the relationships hold, you have things like partial orderings. Partial orderings are we have them or we're able to rely on them thanks to the fact that we have binary relations that will help us to establish uh, those types of either establish or confirm those types of relationships. Is that clear?
Yes.
Okay, that was a hesitated yes. How many people get this 100%? All right, show of hands. Okay, so Evan gets it. By the way, option Y or alt Y. That's how I see your hand. Um, wait, somebody put a thumbs up, but I didn't see who. Okay, so right, Ryan, Han, Saber, George. All right, Kevin, Jahid, the other Jahid, Mr. Ula, and Mr. Hassan. Great. All right, so now I had to ask about Nafiz and Shafi. How can I help the two of you?
Oh, I put a thumbs up, but apparently it went down pretty fast.
Oh, okay. Yeah, those go down quickly. So Nafiz, how's it going there?
I think I got it, Professor.
Okay, great. So now let's get back to what we were talking about. Evan, given your example, can you now apply the same type of principle to sets that you applied to integers?
Yeah, let me try. Let me look.
Okay.
So Okay. Let me think what a so um, would it just be P of S would look like P parenthesis S like on that on the left side, and the other side would just be P being multiplied onto the set of B, C, and D?
Hmm. Okay, so here's what it is. So a power set, you ready?
Yeah.
It's the set of all subsets. And in order to include the set of all subsets, you're gonna have to have the list of every subset of each size. So that includes the subset of size 0, which would be the empty set. Remember how I said that if it were just like, the empty set, then we wouldn't call it a proper set because it's not really like, a set that is a strict subset of the larger set. Instead, it's
Is this
just like,
like my bad, I'm really sorry. Is this like related to factorials, like the idea of like expanding it out to all the possible subsets and then multiplying that together?
close, but not quite. It's relate.
Okay.
So here's the thing. Later on, we're going to talk about exponential functions. And taking the power set of all possibilities, that's one of our brute force methods. So that's why I used a very small set and asked you what the power set will look like, right? So ultimately, you're going to have 2 to the n elements in that power set. So since S has a size of 3, right? B, C, and D, those 3 elements, you would actually have 8 different elements in your power set. All right. So you would have each of these 3 individual letters, right? That would be 3. You'd also have each pair of letters, right? So that would be BC, CD, and BD. That's another 3. That's 6. Then you have the empty set, which is 7. And then you would have the entire set, which makes 8, 2 to the third. So that's what the power set P of S would look like. Is there a partial ordering property on S given its subsets? Explain. So in this case, the answer would actually be yes, but the reason why is because remember what I said about the binary relationship that is a subset. So you can actually, rather than using less than or equal to, you can check to see if given any 2 subsets, if they're subsets of one another, right? So that's why I said, if A is a subset of B, B is a subset of C, is A a subset of C? Yes, it is. So if we had to put things in order based off of, what's a subset of what else, that would be possible, right? That's a total possibility. So what is the brute force or naive method? What time complexity would it fall under and why? And this directly follows from the above question, by the way. Anybody? Wow. Anybody?
Oh, sure. Right. So the brute force method is where you exhaust all possibilities
Hmm?
instead of going through a more organized and surgical way to try to get data. In I think the time complexity it would fall under would just be O of n because you have to do as many steps as there are pieces of data in the set. And a great example, I think, of a brute force method is doing a depth first search through a binary tree and going all the way down every single um, branch of the binary tree.
Hmm. Okay. Uh, the brute force or naive method. This is the one where we try everything to see if it works. The time complexity it would fall under. Well, that would be the exponential class, like to the n factorial. All right, any questions? Okay, Evan.
Yeah, so what's like an example of like or just like or I guess like the why as to why it's in the exponential class, just in order to kind of get that all squared away.
2 to the n? Why is it an exponential class?
Yeah, why is it exponential? Or
Well,
you know,
normally when we have a class that is in um what's to the exponential class. All right, it's an exponential class because it requires that we find all that we listed the superset of a given set. And by listing it, we're taking, details that are perhaps old or um, that may be obscure. And then we're using it to bring, I guess you could say, some sort of order or experimentation out of it. So brute force and naive methods, they have to do with us not using a cleverly derived algorithm. Okay,
thanks.
so now, yes. Oh, question?
Well, no, I was just saying thanks because I understand it because right, like yeah, that makes sense because you have to try literally every single combination of that set, every subset, um, which would be exponential.
Great. So now here's a very tame question for you. What is an algorithm? What are data structures? And who partially, or order, why do partial orderings matter in the early of both? Why do both of them not matter? Any answers? None. Okay, Evan.
So, uh, an algorithm is a set of steps in
Hmm.
order to complete a specific problem.
Hmm.
Data structures in computer science are quite literally just different ways to store data in computers. Um, a good example would be something like an array where there's a fixed length, at least in Java. Um, and there's, different data structures have different benefits and drawbacks for different purposes. Partial orderings matter in the study of both algorithms and in the study of data structures because partial orderings are relevant in algorithms as like basically just laying out the specific steps to do. And in data structures, partial orderings matter when it comes to actually representing the data within a data structure.
Okay. All right. Other questions or other takes of that. Everyone agrees. All right, that's not necessarily the case there. So here's the thing. When it comes to an algorithm, it's a finite sequence of steps that serve as a solution to a given problem. Now, when it, let's see, what time complexity would it fall under? Number five, brute force method means you're trying everything in hopes that something will work. The time complexity would fall under uh, the exponential time complexity, basically, right? So what's an algorithm? What are databases? Order, why would partial orderings matter in the study of both? Okay, guess I'll wait just a little longer.
Could you say the
Okay,
full question again? I'm
say that
sorry.
again.
I'm sorry. Could you say the full question again? What you're
Okay,
asking? Just to make
so
sure I have it correct.
the brute force and naive method, what time complexities would it fall under and why? You have anything?
It would fall under, I believe, little O notation. Isn't that?
No.
Shit.
Okay, exponential running time. Because you have to try all the different possibilities. If those possibilities were based off of sets, chances are you're going to take the power set or something and search through it, and that would be exponential running time. Same thing for factorials; those are exponential running times. Who gets it and who does not? First, who gets it? Just see the hands. One, two. Okay, just two people. Questions, y'all?
Sorry, I had to use the restroom. Which question were we going over? Number seven?
Uh, six.
Six. Could you go over the third part? Why do partial orderings matter in the study of both again?
Okay. Do partial orderings matter in the study of both? Because they allow us to set up a partial ordering property where we can actually and um, systematically relate one object to another. So remember I said that if we created a power set, it would be 2 to the n, where n was the actual item that we were watching out for. And now we have the rest of our journey uninterrupted. Any answers? None. Okay, I'll leave that one on the cutting room floor for now. What is an algorithm and what are data structures assumed? All right. So what's an algorithm? What are data structures? Why do partial orderings matter in the study of the booth?
Uh, an algorithm, I think, would be a series of instructions that would, or a series of processes that would just solve a problem. I'm not sure exactly what else could be said.
Hmm, okay. So
Um,
here's, yes.
sorry. Uh, I guess I wanted to answer data structures. Could you say they're like an abstraction to organize data or like elements in a certain fashion?
Where do you get organized data from?
I would say data structures are like the structures that hold data, such as lists, arrays, trees. It would be like how we store and how do we go, like, how do we search through it and how do we travel through it?
Okay. That happens at the beginning. Anyone else? Okay. I'll open the floor to anybody. Well, an algorithm, finite sequence of steps to solve a problem. Data structure is a program used to simplify input data for the sake of the processor.
Oh, can I ask a clarifying question?
Yes.
So, like, what in that definition refers to data structures as like a, when you say like a program, does that mean
Container.
like a container, like like an like an object, right? Or an instance that holds data types?
Um, no, not quite. Not quite. So
Because
now, go on
I
ahead.
was a little confused because I was thinking of a definition to just describe like a stack or like a heap or like a first uh I'm trying to think like a any sort of data structure. And
Hmm?
when I was trying to describe it, I was like, oh, so it's like data that is organized together and has certain relationships. That's an abstraction of like a container-ish. So, but I don't know where you would get like a program or I don't know.
Okay. All right.
Oh,
You know,
okay, I think I
uh,
understand it now a little bit better.
all right, let's see. So let me just go back a couple times.
Sorry to cut you off. The
Yes, sir.
document that you shared in the chat, it's
Mhm.
only showing the first part up until transivity. This first part, yeah. It doesn't show the other questions
Let's see.
for
Okay,
the re.
so this one right here, um, let me just, that one right there you're talking about?
Yep,
Okay, what
it's
other
not in the
questions are
file.
you asking about?
Oh no, like the document that you shared is not included. Oh, you're not
Let me,
sharing this?
I put it in the chat, remember?
Oh, but it's not. It's only showing up to the first part, like not this part.
That's
Uh,
odd. Wait, does everybody have that problem?
I only have refresher one.
Yes.
Yeah, same
Oh,
here.
wait, if it's refresher one, hold on. Let's see.
Don't have practice exam one in the chat.
Uh,
Or did
yeah,
you
that's
upload in
fine. That's
Dropbox?
fine. This isn't even yeah, it's gonna be on the Dropbox, but this isn't even finished yet. So
Oh, okay.
right. So now that's why that's there. But let's get down into the answer. So this was from day one. All right. And here we go. A container for data to store the items in a formally specified construct is what we call the data structure. Its purpose is to prepare collections of data for efficient processing by an algorithm. An efficient algorithm always relies on the identification and use of ordering properties to allow us to safely and correctly skip steps. Efficient solutions are known to exhibit a partial ordering property in either the container, data structure, or the algorithm. That's why we're not doing brute force with everything. Does that make sense? For what are data structures? What is an algorithm? What are data structures? Why do partial orderings matter in the study of both? That's the key part there. All right. If you want to see that, hold on. Let me open up the chat and I'll throw it right on in. Okay, so let me throw in, let's see, this is transition to data structures. Let me throw that in. And there you have that. And let's see. Also tree based. That's another file. Okay, y'all with me? Let me just see the participants, make sure everybody's with me. And let's see, Evan, do you have a question or are you with me?
Oh no, I just want to say I was here and also thanks for posting the documents.
Sure, sure. Okay, so how many people get that last part that we were just talking about? What's an algorithm? What are data structures? Why do partial orders matter in the study of both? Everybody gets that? Who does not get that? By show of hands. Evan, you don't get it.
I get the first two parts, but so why exactly do partial orderings matter for both of them?
Okay, so here's what we said, remember? So let me just put the chat away and minimize this. So here goes. An efficient algorithm always relies on the identification and use of ordering properties to allow us to safely and correctly skip steps. Efficient solutions are known to exhibit a partial ordering property in either the container, the data structure, or the algorithm. See both of them in there? So let's suppose that we're talking about, partial orderings with binary search, right? And we did the whole thing with a sorted array. We're jumping in the middle. right? We know that it's already sorted. So on the left-hand side, if everything on the left-hand side of the array is smaller than whatever item we're looking for, we can then throw out that half, and then we do the same thing. We check the other side and start trying to jump into the middle to see, hey, greater than, less than. And before you know it, because we have a partial ordering property, we're able to actually, find what we're looking for faster because we can assume certain things about the partial ordering that will allow us to understand that, we are moving a bit faster based off of those preconditions. And that by means of that, we're able to skip steps. And skipping steps means that we're able to work faster, but only if we skip steps correctly.
Yeah, the binary search makes it make a lot of sense. Thanks.
Okay, cool, great. So now add to this the following, because you see, we did that in an array, right? But now if we did it in a binary search tree, it would be slightly different. You see, with the binary search tree, everything is stored in a given node based off of the partial ordering, right? So it's not that we have a list that's sorted. We know that the tree has a partial ordering property between the positions of the nodes. So then being able to find what we're looking for means that we can traverse the different nodes back and forth based off of greater than, less than, left or right, and then find what we're looking for without searching the entire tree because the partial ordering property is within the actual data structure there. Within the case of the binary search within the array, the actual partial ordering property was within the algorithm part, not within some container. So when we have different algorithms, we usually have a partial ordering property that we establish that allows us to skip over to, other parts of our problem without having to search everything in sequence, right? So that brings us to this next question here. By way of example, is binary search faster than sequential search? Why or why not? All right, so you guys should be able to give me an answer to this one.
It is faster
Okay, why?
because sequential search, I'm assuming sequential search is just going in order, like through each element.
Hmm,
A binary
okay,
search is actively skipping elements and reducing the size that it has to go, of the array that it has to go through.
right, the elements that it has to search through. So a sequential search, if we have n elements and we're not finding them too quickly, we have to search through n of them. Let's suppose that we were never going to find the element we were looking for, right? Well, then what that means is that we would search for the entire list of items, all n of them, find nothing, but waste all that time. With a binary search, we know that everything is sorted. So if we don't find what we're looking for in log n time, we know that it wasn't there, and we don't even have to look at each element. So that's why it's faster. The sequential search is a case of brute force. There's no precondition that gives us, a partial ordering that we can rely on. With binary search, there is some sort of partial ordering inherent in our use of it. And so that allows us to rely on, that property so we don't have to go through the brute force method of trying every possibility. Now, normally when we do brute force methods, we either search through a power set or through a permutation. So we could be looking through as much as 2 to the n or even n factorial different items, right? We don't want to do that because that's what we call intractability. As it grows large, those types of problems are going to be larger than any other problems that we will usually find in computer science. So that's why we're talking so much about time complexity. So that answers this part right here. What is brute force a naive method? What time complexities would it fall under? Why? So if it's something like a linear list, then it's going to be n, right? Because we got to do everything. But if it's not that, if it's like some sort of combination or some sort of configuration, then it's going to be like 2 to the n or n factorial. Remember the part about the power set? That was 2 to the n? Yeah, brute force. We're listing all possible sets. We're just doing things exhaustively. We're spamming, basically. Don't put spamming on the test, though. It's not like technical talk that, it's not respected in scholastic circles, I don't think. But we're really trying everything with no real direction. So now, given that, okay, let's talk about some definitions here, more definitions. So can you define the following? Let's see. Just going to come down here. Right, so let's suppose that you say that this define the following. Okay, and we have big O, and also little o. And then we also have, let me just insert special character. All right, so we also have theta. Insert that. Okay. Also insert another one. Where's my special characters again? There we go. Right. What about, say, omega, big omega, and also where is my, there we go, special character right here. And also, there we go, little omega. All right, can you define the following? We say that that a function f of n is in big O of n if and only if, you remember that one? All right. Also, so if I say give examples, could you? Here's a good way to think about it as a hint. That chart would help you out. The one that we did up top, that would help you. Okay. Now, let's see. Um, Now, not all of these are going to appear on the exam, so I'm just going to pick from them. There are some that I would like to put on the exam no matter what. The first one, definitely. All right. Something else I'd like to put on the exam. Let's see. How many of you have become comfortable with the master theorem?
I would say I get the general premise of the master theorem. So I don't know what questions you would ask about it.
Yeah, I agree.
If I gave you a recurrence relation, could you tell me, or could you, tell me the actual complexity of it? Let's suppose that I didn't do that thing where it falls through the cracks with a special case. Would you then be able to, tell me the complexity of the recurrence relation? Okay. All right. So let's see. We have quite a few things that are good for us to discuss. Um, I would like for you to be able to do one induction proof. Do you think you could? I'll make sure that there's no funny polynomials, but could you do an induction proof if asked? How many say yes?
Yes.
Okay,
Yeah.
Kevin says yes.
I think it'd be good, yeah, as long as there's no like really bizarre polynomials.
No,
Um,
all right,
Will it be open book or no
like
for the
double
bullet?
digits is fine, but triple digits was,
all right, all right. Um, Open book. Well, okay, so we had this question before. So if it's open notes, then the answers won't be as straightforward. If it's closed notes, then I'm not gonna like, fire up stuff or anything like that.
Because for induction, I feel like I need more practice. It's been 3 years since I went over that.
But
Well, I
remember,
did discrete math.
there's only three steps though. The first one is the basis step, right? And
Mhm.
then there was the induction step. And so, but the basis step, you just got to show that, um, given the smallest case, that the principle is true. With the induction step, you show that first, for an arbitrary case, the general statement is true. But once we take statement or case and then transition into the next case, you see that in the next case, the relationships hold. And when you do that, that's the induction, proof that allows you to prove the remainder of everything for, however whatever sequence of principles you need to prove them. Right. So I think that there's a lot of good ways of uh let's see, show that show that if I ask you to show me that n is greater than log base 2 of n for n greater than 2, could you do that? Or if I ask you to show me that, 2n is greater than log base 2 of n, right, for choices of n that are integers, greater than 1, could you do that? So the basis step, you're saying, oh, well, log base 2 of 2 would be 1. And in the case of 2n, well, then 2 times 2 would be 4. So that checks out. and then you look for the next case, right? So log base n of, like 4 or something like that, compared to 2 times 4, and you start, showing that it doesn't take off faster than, 2n or something to that effect. If I asked you about 2 to the n versus n factorial, then what? So let's suppose that we had something like show that 3 to the n is less than n factorial, okay? Um, for n greater than, all right, and I'm going to go with, let's see, uh, let's see, is that the case for 7, maybe? Let me break out my calculator online. All right, so let's see, 3 to the 8
Would we be able to use a calculator during the exam?
Uh, no, that's why I'm going to give you a very, very small one.
I see.
So 3 to the 8 would give me, I don't want to turn that on. Don't turn on. So 3 to the 8th would give me this, right? And now 8 factorial gives me that. 3 to the 7th gives me that. The 7 factorial gives me that. Let's try that again. 3 to the 7th. 3 to the 7th. Okay, so let's just see. 3 to the 6th, is that the cutoff? 3 to the 6th, 729. And 6 factorial would be 720. So for n greater than 6. All right, so I'm going to do this one myself. And so now for the basis step, we'll see the following. Basis. All right, 3 to the 6th is actually going to be just put in 3 to the 6th. Yikes, wrong one, pressing the wrong keys. So 3 to the 6th is equal to, see, that'll be, see, 3, 9, 27, 81, 243. So that would be 729. Um, I'm sorry, so it's supposed to be 7. Let me put the 7 in. So 7, all right? So instead of 729, it would be 2187. So it equals 2187. All right. But as for 6 factorial, or I should say 7 factorial, because it's the basis, and this is n greater than 6, right? So 7 factorial equals 540, or 5040, I should say, right? So that checks out. Now for the induction step, we have the following. So in this case, we want to show that as long as k is greater than 7, that is still going to hold, right? So for k greater than 7, we're going to do the following. You have 3 to the k plus 1, right? So as 3 to the k, it's going to copy this over. And I'm going to come up here, put the k there. That 3 to the k is less than k factorial for k greater than, or k greater than or equal to 7. Let me just put in my special character. I need to say less than or equal to, where is it? There we go. That guy. Oh no, I should have did the other one. My bad. Sorry about that. Greater than or equal to. So for k greater than or equal to, I should be saying 7, not 8. All right. Then 3 to the k you're going to put in some plus 1. And this is also going to be plus 1. Is what we set out to prove. So let t of k plus 1 equal this statement right here. And I'm just going to put up here, this is p of k, that right there. Okay, but now let's take a look at the relationship between P of K plus 1 and P of K, all right? So here's how we do this. We're going to turn both of them back into cases of their former selves. Just gonna do this like that there, okay? That way I can put a period here and not confuse people. Or better yet, well, yeah. So now the next thing we say is the following. But 3 to the K plus 1 equals this here. This equals 3 times 3 to the K. All right. Now, likewise, okay, K plus 1 factorial. And I'm just going to come over here and I'm going to put in something that looks like that. That way we don't forget that that's point number 1. Likewise, and now we're going to work on point number 2. K plus 1 factorial equals K plus 1 times K factorial. All right, so now we have these new terms that we've separated from the old terms. This was the left-hand side. Well, let me just put in 2 right here. Okay, so now this guy over here was the left-hand side of P of K. And this guy right here was the right-hand side of P of K. And now these are the new terms. So now here's where it gets even more interesting. Anybody want to chime in? No, I should just have all the fun by myself? Okay, okay. So now, here's what happens. Take a look. But now we already said that for K greater than or equal to 7. So in this case, if K is greater than or equal to 7, then K plus 1, I think we all know this part. This part is going to be greater than or equal to 8. Okay, now, given the new terms, so on the left-hand side, we'll say the following. Since 3 is clearly less than 8. Then multiplying the new terms are not going to reverse the proportionality, right? So then as T of K is true, then we're going to say that 3 times, or we're going to say that 3 to the K plus 1 like this. Just gonna copy this over. Is gonna be less than 8 times K factorial. Which for its own part equals K plus 1 factorial. So now, take a look. This guy here is less than this guy here. All right. So now I'm gonna put this here as, just gonna put a notation that says 4. And I'm gonna come over here and I'm gonna call this 5. All right. So now, since we have that there, we could say that we now know that 1 is less than 2. Well, let's see. Do I have to really do that? I can, since I didn't use this here, I could just take the 1 out and the 2 out. I could relabel the other ones. Okay, so this guy there and this guy here. All right, so given 1, and this guy here is 2. I should probably just come down 1 line. And I guess this will make it a bit readable, more readable. Okay, so like that. Okay, so we know that P of K plus 1 is true. So now we could say the following. Hence, P of N is true. For all N greater than and I believe the answer was 6. For all N greater than 6. And that concludes the proof. So now, why is this important? Let's suppose that we have an algorithm that runs in 3 to the n time, and we have one that runs in n factorial time. As you remember, um, as our functions grow large, that's when we become concerned about which one is the larger of the two. So if we had to compare an n factorial algorithm, one that runs in n factorial with one that runs 3 to the n, we know that the 3 to the n is the lesser evil of the two, given this particular basis, because if n is anything greater than 6, then n factorial is going to take off in a much larger way. Okay. Now, I won't be giving you this exact one here. I'll probably change like the number or the terms, but it will much more likely be the same, right? It'll be very similar. So there you have it. Let's see. So let's see that would be, I imagine for this here, I would give a whole lot more points though for this proof right here. And that's the last, okay, so the last thing I want to do is the following. So compare and contrast the advantages and disadvantages of the following. This is something you should already know. So let me just put in a table. One second, I'll be right with you. There we go. All right, so here we have VS. All right, and here we have heap sort, merge sort, quick sort. And the same thing over here. Okay, and so clearly there'll be nothing to put in these diagonal boxes. All right. Now, Nafis, your hand is up.
Yeah, Professor, sorry, where do I find the recordings again?
I'm gonna be posting them up today. So, like you'll be able to use them over the weekend, like starting this evening to the weekend.
So will it
Just
be in the
like,
Dropbox?
no, YouTube, my YouTube channel.
Okay, okay. Thank you.
Sure. Um, let's see. So now, this is heap sort, merge sort, quick sort, heap sort, merge. So now, if we compare heap sort with merge sort, both of them are running in n log n time. What can we say about the advantage of heap sort?
Does heap sort use less memory than merge sort?
Okay, great. Right. So merge sort, what would you say about merge sort then? What's the disadvantage? You would say what do we call that when it uses memory during its execution?
Space inefficient?
Well, okay, so it has an associated space complexity to it that heap sort does not, merge sort does not run in place.
Okay.
Okay, what about heap sort versus quick sort? Heap sort versus quick sort? Okay, well, heap sort runs n log n, and while quick sort may run in n squared worst time, the expected case of quicksort is actually n log n in just about every case, in most of them. What's more is that quicksort runs faster to a constant factor compared to heap sort. Also, quicksort is better if we don't have much memory. So quicksort runs on using very little resources. Now, what can we say about uh, quicksort versus merge sort? I mean, basically, all I have to do is combine the other two together, right? The last two explanations. All right, but that's basically what it is. And any questions? Okay, so let's see. That's, I think we have quite a bit here. This is good. When it comes to big O, if I ask you to find the C, the N, and the N not between two algorithms that makes big O correct, could you do that, students? Yikes. How many for yes?
I'm sorry, could you repeat what you said?
So given the definition of big O notation, if I ask you to find the numbers C, N, and N naught, could you?
I'm sorry, I did I don't really think I really knew exactly what that meant. My bad.
You're bad. Okay, let's take a look again. So in our, let's take a look at the book. Growth of functions. So this is theta, right? But I think big O is easier to work with to some degree. O notation. So we say that O of G of N equals F of N, such that there exist positive constants C and N naught, such that F of N is somewhere between 0 and C times G of N for all N greater than or equal to N naught. So if you had to find the N naught as well as C, could you? Let's work on an example. So is 2 to the N plus 1 equal to O of 2 to the N? Is 2 to the 2N equal to O of 2N? All right, so let's see. I don't, what I want to do is, let me see if I can give you a more concrete case though. So I'm sure there'll be somebody who has like a good example. Big O example. No, that wasn't the best. Okay, so take a look. So if f of n equals n squared, and g of n equals n cubed, and h of n equals n to the fourth, then f of n equals O of g of n squared is in O of n cubed, and g of n is in O of h of n. So by transitivity, f of n is in O of h of n. Now let's take a look at, let's see. Actually, there wouldn't be much good there because after, for any integer greater than 1, then it starts to take off. So let's see. Okay, I'll go to that other example that we had up above. So the 3 to the n and n factorial, that was a fair example of the whole thing in progress, right? So at what point does 3 to the n overtake the n factorial? So we said for n greater than 6, right? Um, Now n is supposed to be a natural number. However, c does not have to be. It's just a constant, right? So now imagine that we have 3 to the n and n factorial, right? Given the constant, do we know at what point our n naught begins? Well, if n naught is an integer, right, then our n naught begins with 7, right? So for all of these things, for 7, that would be our n naught. And for any n greater than 7, this whole thing holds, right? Now, it wouldn't matter what the constant is because, even though at this point the constant could be 2 and still 7 factorial is greater. So the n naught would be 7. And, that would allow us to show that by way of big O notation, we can believe that 3 of 7 is in O, or 3 of 7 equals big O of 7 factorial. Or it allows us to say that, 3 to the n equals big O of n factorial. Make sense? The n naught is 7. Okay, questions? Mm, No questions. So if I pick questions from here randomly, you're all good at what we have here. You'll be just fine.
Honestly,
Everyone,
no, but crossing my fingers.
honestly, no, but crossing your fingers. Why would you say no?
Need some more practice, like especially for induction. If it's similar to this, then maybe, I mean, it depends, like how comfortable I am with. I need to practice this more.
And you can't really see how you're going from k to k plus 1. This is k. This is k plus 1. Here's the relationship between the two. This is k. This is k plus 1. This is the relationship between those two. Then you see that given this, k plus 1 must be 1 plus both sides of that. But given that, that reality, we know that, multiplying by this does not really overtake the fact that k plus 1 is so much larger.
We got 3 to the 7 because of the condition n is greater than 6, right?
Uh-huh.
Okay.
That was the basis that it would not have
Okay.
worked for like 0, 1, or anything else. It would have to be 7 at least. Okay.
Okay, I
So
got it.
so the master theorem part. Is everybody good with that? Do you know how? Do you understand it? Or No.
What's a question related to that you would ask?
Well, let's suppose I give you a recurrence question, right? Could you tell me what the actual um what the actual running time would be if I give you a recurrence relation? So let's see. Right here. Right here we have a recurrence relation. But going beyond the substitution method, the master theorem helps us with the recurrence relation because it says the following. You have A greater than or equal to 1 and B is greater than 1. Those are the constants. Let f of n be a function and t of n be defined on the non-negative integers by the recurrence. T of n equals A times t of n over b plus f of n, where we interpret interpret n over b to mean either n, the floor of n over b, or the ceiling of n over b. Then t of n has the following asymptotic bounds. F of n equals O of n to the log base b of a minus some epsilon, for some constant epsilon greater than 0. Then t of n equals n to the log base b of a. In other words, if f of n is smaller than this guy here, if f of n is smaller than the term that we get from this guy here, right? The one that we're going to choose is it's going to be theta of that particular O of n to the log base b of a. However, in the event that f of n is equal to theta of it, in other words, f of n is growing roughly at the same rate, then t of n is going to be equal to theta of log base b of a times log of n. T of n is going to be equal to, that particular part of our function. Now, if f of n is in omega, meaning that f of n is larger than n log base b of a plus some epsilon for some constant epsilon greater than 0, and if f of n over b is less than or equal to c of f of n for some constant c less than 1, all sufficiently large n, then t of n would be in theta of the second term. So larger, second term, smaller, log base b of a, first term. Right? It's in theta of the equation derived from the first term. Otherwise, it would be this case here, right? The first term times log of n. All right. Now, notice that the numbers, the polynomials, have to be either smaller or greater. Right? That's the part that, we have there where we wonder about, well, is it smaller or greater? So that's why we have the examples that come next using the master method. In this case, we have n, and here we have, this is a, and that's b. And so now we're wondering, hey, well, if n is less than n to the log base b of a, n to the log base 3 of 9, well then what does that leave us with? Well, n is indeed less than n to the log, or it's less than n squared, basically, right? So then the running time is going to be n squared. Ct of n equals theta of n squared, the running time of the first part. Now, in the event that it was something else, like say this part here, right? Now we have a different issue. So now this is one constant time, and then this part right here, the b, would be equal to 3 over 2. All right, and the a is equal to 1. So log base b, log base 3 over 2, which isn't necessarily the easiest thing you'll ever do in your life, but base 3 over 2 of 1 equals. Now we know that of any base, right? The log of 1 would be 0. Raise any number to the power of 0, and you're going to get a 1. So that's how to get n0. N0 equals 1. But now if that's the case, then you have 1 on one side and then 1 on the other. So by comparison, now you have to have 1, and let's see, 1 times log of n, basically, right? So let's just take a look. That would mean that we have log of n as our running time. 1 times log of n. Log of n is our running time. Let's take a look at what they gave us here, theta log n. Now in this case, you have 3 times n over 4, and then this is n log n. So now log base b over a would be log base 4 of 3. Okay, now log base 4 of 3 is going to be less than n log n. So the running time would be n log n, or it should be theta of n log n. Let's take a look. My mistake. It falls into the gap. I won't be doing that for the exam. Let's see. This one. This is n for f of n. And this log base 2 of 2, that would be 1. So now n to the log base 2 of 2, n to the first is n. This is also n. So then you have n log n as the running time. Here we have log base 2 of 4. And here you have n squared. Now log base 2 of 8. So that would mean that what we have here on the left-hand side, we expect a running time of n cubed. Over here you have n squared. So the answer is going to be that this is in theta of n cubed. Which is what you have here. Now this would be log base 2 of 7 versus versus n squared. Log base 2 of 7 is just slightly smaller than log base 2 of 8, which would be n to n cubed, right? So now this one is slightly larger. And so we would expect a running time of theta of log base 2 of 7, which is what you have here. Okay, any questions? Everyone good to go? So you're basically choosing between the theta component for f of n or the actual computed logarithm, the calculated logarithm of the first term. And you're choosing the greater of the two, or you're choosing the first log n of Yeah, if they're roughly equal, then you're choosing that running time times log n. Everybody get that? Who does not get that? Okay, who gets it? Who's just fine with it? No show of hands today? All right, students. Okay, we got Shahid Hassan says thumbs up. Who else?
I get the idea. I'm gonna do some practice of the master theorem. I did some earlier. Um,
Cool.
but it actually is really helpful what you just said about like basically picking and choosing um either the first half or the second half, depending on which one is greater
Mm-hmm.
for the for it.
Right. And so all you have to remember really is this is B, that's A, log base B of A, and it's going to be raised to the log base B of A. And you have to make sure that whatever you're choosing, it's not because the values are equal. So if this were n squared and that were n squared on the right-hand side, then you would not pick, you know, the left-hand or right-hand side. Instead, if this were n squared and this one were n, then you would pick the left-hand side. If this were n cubed and this happened to be n4, the right-hand side, right? So they can't be in theta of the exact same running class. They have to be like polynomially larger or smaller. And that's how you do it. So if this guy here, if his log base b of a is larger than this simple term here, then you choose the log base b of a part of this one here. Otherwise, you would choose the right-hand side. Now, if that doesn't work, then you would choose the log base b of a times log n. All right. Everybody feel a bit more comfortable with that? Now, if you don't feel so comfortable with it, remember that we talked about recursion trees. The proof of the master theorem should help a bit more. That way you can see why, the tree leads into us being able to conclude with the master theorem. So if that helps, feel free. Okay, so questions. Let's hear them. Yes, I'm posting this up soon. Anything else?
Out of curiosity, how long will the exam take to complete?
Okay, so one, I'm going to be picking questions from this pool here, and whatever I give for you to do, it's going to be, the way that I normally do it with the whole time thing is that I would give you enough time where for me, I would be able to do the same thing 2 or 3 times faster.
Okay.
So if you have, say, 90 minutes to do it, that means that whatever I gave you to do, I could do in 30 to 45 at the worst, right? If I gave you an hour, then that means that I could do it in 20 to 30 minutes at the worst. So that's how I usually scale it. Like you get 2 to 3 times as much time as it would take me to come up with the answers. Does that make sense?
Yeah, that makes sense. You also mentioned you're taking it from a pool. So does that mean that you're taking it from the pool of the problems at the end of at the end of the chapter? Is that a reasonable pool to look at questions from?
The practice exam is a reasonable pool for you to look at.
Oh, okay, okay. I got a little confused there. I've been looking at the practice exam, of course, the whole class, but
Right,
um,
right. So not all of these will be on the exam. I'll be choosing amongst them, but many of them will. and others will be, left out. Somebody asked in another class if they could see how my exams stack up, right? Here, I'll show you what I did in other classes. That way you can see exactly how I usually relate the exam to the practice exam, right? So let's suppose this with database administration. And this for database administration. And let's see, maybe I should show you using my stuff on, wait, I think I might have it on my actual machine. Let me see if I have it on my machine. Mhm. Mhm. Oh, okay, here goes a good example. So I have a question pool for another class that I did some years ago. And I also have the actual final exam that I gave them that I selected from the question pool. Great. This will be very exact. So now let me just minimize this here. Now, the only thing I didn't put on the practice exam is a master theorem question. I'll probably throw one in there or something to that effect. But other than that, you pretty much have the entire question pool. So now here we have final exam, and here you have the question pool. So here I have things like which tags, notations are required to build a basic web page in HTML5, what HTML elements are used to add sounds to a web page, add movies, add pictures. As you can see, all of these here, this is my question pool. It's somewhat larger than anything I would give the students in the actual classroom. But my question pool is what I build up over the semester, right? Now, if this class were longer, I probably space things out with different exams, and then the question pool would build up more slowly. But now, if you take a look at the final exam, this right here, which tags are required to build a basic web page in HTML5? By the time that was on the exam, they would have seen it in the question pool. What about sound or movie or pictures? Right, they would have seen that in the question pool. Doesn't mean that everything in there made it to the exam.
I see, I see. Thank you. That makes a lot of sense.
Okay, so now that's how I do things. Um, I can pick from them. Only if I had a very small pool would I pick everything, right? So that's usually like if I have a longer semester and I was able to have an exam one would probably be, you know, almost like side by side the same. But as it gets, as things get a bit more, how would I put it, elaborate, then, compared to the question pool, it's going to change a bit. Let's see. If I can find my databases stuff. So in databases, here I have an exam. And let me just see if I have where are my exams? My exams, my exams, my exams. I might have to search for it in or let's see, databases. Databases. It should have something in here. Let me just look at exam. Exam. Mm, and it should also be like a doc file. No. You know what? I think I can use operations management as an example though. Operations management. In fact, I think I have plenty of there we go. I should have plenty of them up here. I can show you what I had in other classes and database administration, practice final. The practice final has all these questions here, right? Doesn't mean that they all made it on the exam though. My actual final exams, do I even have one up here? Uh, I may have some from previous semesters. So you should be able to see that when it comes to the exams that I gave, they usually were a lot like the actual questions um in the review material. So I try to make sure that that they're actually they mirror each other, but you have to know the work. That's how I do things. So here was an actual final exam. And as you can see here, this part with A minus B, A intersection B, A union B, A cross B, you would have seen that elsewhere, right? Take a look at that part there. And now I'll show you how it was in the practice material, all right? And what's more, some of the questions were already on previous exams, so it's cumulative, right? Let me just see. Right, so it's cumulative. Some of these things that were old questions would also be on the final exam sometimes, whereas new questions may or may not be, And so as the pool builds, I just pick randomly, but you should know everything from the pool. And that's what it is. Um, so yeah, the practice final, as you saw, I showed you the thing with the A cross B and the A minus B. And so here it is again, A, B, and A cross B, you know, those are there. Um, right. So, oh, let's see. No, that's not A minus B. That would be mutex. All right. But yeah, as you can see, they're largely there. Which join gives me the following from a Venn diagram? That was a question previously. Um, so yeah, that's how I do things. Any questions? I mean, I could show you from another class something similar. Um, let's see, what did I do in C++? Are my exams up here for C++? I do have, what was the practice put for, okay, final exam study material. So the previous exam looked like this here. In fact, you even have some of the materials for your exam. But what did I put in the second part? Difference between vectors and arrays, cubed and others. But let me just see, where did I put the actual exams up? Uh, hmm. The actual exams were recap with it. Um, might have been, but as you can see, I usually like get pretty thorough about um making sure that the two are reflected in one another so that there's not a bunch of people going, oh well, I felt like I got faked out, or the exam was unfair, or I got, I want to complain. By the time you feel like that, you should also feel like, you should have done something a bit better. So, that's what that is. Um, Design and implementation, I think my e-business or my operations management stuff would also, um, there we go, operations management. I have plenty of these. So exam 3 versus, let me see if I can find a practice final or a final sample exam. Okay, so yeah, here we have like what one of the exams was, but now the practice exam, well, no, let's see, how long is it? Okay, this is a pool. This is an example of a pool. Okay, a question pool is right here. Now, if you take a look at the question pool, let's see. Why is business process re-engineering so difficult to accomplish? Why are Kaizen events more practical? And then you'll actually see that for some of my actual exam questions, why is business process re-engineering so difficult to successfully accomplish? Why are Kaizen events a more practical alternative to implement? I mean, I'm not kidding. Like, I really want you to know this stuff. All right. So that's what it is. Okay. Everybody good?
Yeah, sounds good.
Okay.
Yeah. Is it in the Dropbox already? I remember earlier in the class it wasn't posted.
Okay. So you know what I'm going to do right here, right now? With the exception of the master theorem type question, I'm just going to save this thing. Let me pull it up. And I'm actually going to put it in the chat before I walk away. And with that being said and done, there should be hardly any confusion or complaints left.
No, that's great. Thank you.
And here, wait, hold on. Here we go. I'm going to open up the chat and give it to you guys. So let me just do that. By the way, if you got a WN or WU for your grade or something like that, send me an email. Please send me an email. That way I can know and I can speak to the registrar's office. All right. So I need to know who you are and your situation. For a lot of people, it's because they did not sign the attendance sheet in week one, and I was not able to confirm that they were in the class due to the lack of signing the attendance sheet. But hold on, let me just put this thing in the chat box. So for everyone in the meeting, I want to give you the following. One, schoolwork. There you go. That goes there and sending. All right, you can all now download it. Okay, so please send me that email if if you got a WN or something to that effect. Or if you weren't able to access, if you didn't get an email about being, well, then you might not be here today. But yes, if you were dropped from the course or something like that, send me an email. All right, everybody good?
Yep,
Yep.
all good.
All right, then I will be seeing you on Monday. All the best.
Thank you. Have a good day.
Thank you.
You
Have
too.
a good day.
Likewise. Enjoy your weekend, everybody. And all the best on the exam. I'd wish you luck, but I hope you don't need it.